So this is the fourth video on the study of representation theory of finite groups. In this video, we'll introduce a new structure which we will use to study the representations of groups, of finite groups. And it's the language of modules. So this is going to be an introduction to modules. So, as always, we ask the motivation for this. Well, you probably know from studying other areas of math and physics that whenever you can linearize a problem, it's a very good idea to do so. So, for example, if you're studying Lie groups, then the linear structure that you want to study is the tangent space at the identity. And remember, the tangent space is a linear thing. It's a vector space, and that is called the Lie algebra. So studying the representations of the Lie algebra gives you representations of the Lie group, and you understand the Lie group much better. So the language of modules is, in a way, a way to accomplish that same thing for the study of representations of a finite group. Remember, for finite groups, we don't have Lie algebra, and so you might think, well, what linear structure can I use to study the representation theory of finite groups? And the linear structure that we will use is what's called an A module. So let me write a summary of what I just said. So why? This linearizes the problem of studying representations. You might have noticed that a representation was defined as a groupomorphism from G to GLV, and in GLV, what we cared most about was that it respected the multiplicative structure of the group. But of course, in GLV, we can add things, right? If I have, let's say, phi of G and phi of H are in GLV, it certainly makes sense to consider phi plus phi H, right? Linear operators can be added. But nothing in the study of representation theory so far have we considered such an object, this linear sum. So we would like a way to incorporate the idea of adding these things. Another reason why ultimately the language of modules is very helpful is, especially if you're a physicist and you have studied books like, for example, Howard Georgi's book on Lie algebras and particle physics. There are about 20-30 pages where it introduces the representation theory of finite groups. And you're moving along smoothly, and suddenly he talks about characters. And you can definitely see that there's some structure underneath that produces these formulae for characters. But it's not quite obvious where these equations come from, because you're suddenly considering sums of things when before you're only interested in sort of the multiplicative nature of things. So I think the language of modules makes the study of character theory much more natural. So we're going to proceed with introducing modules in stages, and we'll define them after we've defined a few things. Okay, so first we introduce what's called a K-algebra. So again, K is going to be our field. And so a K-algebra sounds fancy, but it's actually very simple. It's just a K vector space. With it's a K vector space where we can also, with a multiplication, in which with a multiplication in which the scalar multiplication commutes with the ring multiplication. Okay, so I just think of it as just a vector space in which I can not only add, but I can also multiply things. So there's a rule that tells me how to multiply things, and whether I multiply the elements of my vector space or I first multiply them by scalars, it doesn't really matter because they commute. And of course, we can also have a homomorphism between K-algebras, because after all, we have homomorphisms between vector spaces, those known as linear operators. So a K-algebra homomorphism is a K linear ring homomorphism. So do you want to see if your function is a homomorphism for this K-algebra? Well, think of your algebra as a ring and make sure that your homomorphism is a ring homomorphism. If it is, it's a K-algebra homomorphism. Now we have an algebra, we can certainly have a subalgebra. So a K subalgebra is a K sub vector space with all the conditions that a K algebra had. Okay, so we have an algebra. Then our next stage, so this was the first stage, so we'll call it stage A. Stage B, we'll define an endomorphism, or at least the kind of endomorphism that we'll use. So we let M be an abelian group. Then the ring endomorphism of M is a set of ring homomorphisms from M, so epsilon from, well, let me not write that, set of ring endomorphisms from M to end M. Okay. And we have that for script E, script F in end of M, we have the multiplicative nature, the additive nature in the abelian group. We define the addition of these ring homomorphisms. I guess this happens in the ring, this happens in the group. Let's see, is that correct? Yes, it is correct. It's an endomorphism, so it takes an element from your abelian group to another element in the abelian group, so this is definitely addition in the group. And I can also define a kind of multiplication, which is given by composition. All right. Now we can define an A module, where A stands for algebra. Again, I'll be quite anal about some notation, because it will help a lot to be careful what we're talking about. So A will stand for the algebra. So this is a triple. This is a triple of the algebra, the K algebra, an endomorphism, and the abelian group. So this is the K algebra, the endomorphism, and the abelian group. And how will we notate the action of the endomorphism on the group? I've already hinted at that. The endomorphism gets well, it will act in such a way that it acts from the K algebra. It acts on it and returns an endomorphism like that, which can then act and psi of A. So A is in A, and then that can act on M. So usually people make the notation shorter by rather than writing so annoying notation. Rather than replace with simply A times M. Okay, and that's, again, if you know what you're doing, that's okay. But if you're a beginner, then I recommend not doing this sort of thing. This is not recommended. And there's a reason why. Because this notation obscures the connection between the language of modules and the language of representations. We want the idea of the endomorphism, the ring endomorphism, to be present in order that the connection between representation be obvious. Yeah, so we want this ring homomorphism to be obvious because we want the connection to the representation language to be obvious. All right. So we can also define a submodule, an A submodule, I suppose. So what you just do is you pick a subgroup of M and make it stable, or make sure it's stable. I suppose make sure it is stable under action of the K-algebra. And we can also define what we mean by a simple module. An A module is simple if it is non-zero and has no non-zero submodules. So I should be seeing the connection between modules and representations slowly emerge. So we had, for representations, we had these representation homomorphisms. So obviously we must have an analog of that, which will be a module homomorphism. So a module homomorphism F from M to N. These are both I guess M is an abelian group, N is an abelian group, and both of them are A modules. So these are abelian groups. So just by guessing, you can guess what the condition is just from what we know about representations. It must be compatible with the action of the ring homomorphisms. The ring homomorphism took us from the K algebra to the ring endomorphisms, to the ring of endomorphisms that act on the abelian group. So condition on F is that if I have F and I have the ring endomorphism, so the endomorphism that acts on my M, that should be the same as if that. So note that we have the same endomorphism acting because both M and N are A modules. Both, just emphasizing both. M and N make up an A module. In other words, the action of the algebra that will ultimately act through the endomorphism is the same in both cases. And then we can define another concept. An A module is finitely generated by Mi in M, where I comes from some indexing set, if M is equal to, comprises of the set of linear combinations of things that look like this. J is contained in I. And I can be taken to be finite. Okay? So if you can find, if every element in your abelian group, if your elements in your A module can be written by some linear combination, if all the elements in your A module can be written by some linear combination, then which can ultimately be taken to be finite, then your A module is said to be finitely generated. Now, there's now a corresponding theorem that we can prove, or statement that we can prove, namely, if I have, if F is a homomorphism, a group homomorphism from M to N, then the image of F, the kernel of F, are submodules of N and M respectively. I'm not going to go through the proof because in the third video on Mashka's theorem, I proved a version of this for representation. And all you need to do is repeat the same arguments, but imagine replacing the representation phi with the K-algebra, and then you replace the representation spaces with the abelian groups. And that should give you a good hint. So, proof. This is a hint. Watch that video and then make those replacements. Okay. You could also think of the endomorphisms acting on the billion group to be what you replace with phi. So here's a proposition, the reason for this video. There is a canonical bijection between finite dimensional representation of a finite group G over K and finitely generated non-zero Kg modules. Okay, so what is a Kg module? Well, we know what a module is. We've been referring to A modules, where A is a K algebra. So Kg must be some sort of algebra. And if you remember from the second video, we're introducing examples of representations, and I introduced the left regular representation. And if you go back and watch that, you'll find that in fact the left regular representation was got by constructing the group algebra. Namely, we get the algebra and create formal linear sums. And of course, we can multiply things in the group. And so, with a combination of addition and multiplication, using the elements of the group, we form an algebra. Because remember, we used the elements of the group as an indexing set for vectors, for vector space, for a basis of a vector space, and that vector space had a field. And so that's where this K comes from. So in other words, let me write it out. We had some sort of basis vectors, Vg1, that were indexed by elements in the group, Vg2 all the way to Vgn. Okay, and of course this was this was a vector space over some field K. And of course we also had a mapping from the group to the GLV, which could act on this set. And so we can create an element. We can then create linear combinations of these vectors, and we can have the representation act on these vectors. And that structure has the structure of an algebra. Okay, so how do I summarize all this? So what all this says is that I have a Kg module. So let me do this. KG is the group algebra, and M is the module, which is really the abelian group. I shouldn't call it the module, it's the abelian group. The module is the triple. And this language can be then used to talk about representations and V, which is vector spaces. And so how do we sort of make that a bit obvious? So given one language, we should be able to produce the other language. Well, we began with representation, so let's try to reproduce the language of modules. So in the language of representations, we must have a representation, phi, and a representation space, V. Okay, now with phi, phi can give us phi of G, which can then act on V. Now the set of phi G is an algebra, since GLV over some field is an algebra. Okay, so and you can see that with the module we had the K algebra, and then we had homomorphisms that took us to the endomorphisms on M. And so we had this structure. We had a K algebra, which gives us an endomorphism which acts on the abelian group M. And what I can start off with is a group algebra, and I can produce, from that I can also have a phi which acts on V. And did I mention? So remember, if you look at the axiom of vector space, a vector space is also an abelian group. So I hope this is becoming more obvious. I hope I'm making sense. But you should really see the parallel of how you can move back and forth given one language. We had a vector space before, and what you can do is you can forget about the fact that it's a vector space and concentrate on the fact that it's a group. In fact, it's an abelian group. So we can now move from V to V, from V to M. So we're here to go from the language of modules. We'll forget about the vector space structure and remember that it's a group, an abelian group. Then on this abelian group, we need something to act on it. Well, we have the representation, which is a group homomorphism. So where does it come from? So the group homomorphism comes from some G. Well, this phi of G must act on this, must act on what's ultimately going to be called an abelian group. And it can certainly do that because we already have phi of G acting on V, which we're now just considering to be an abelian group. And how do we get this phi of G? We need an algebra. And how do we get the algebra? Well, we have the group here, and then we can use the group to construct formal linear sums of the group elements to produce this KG, or K algebra. And what's the field? Well, we can choose the field that comes from the vector space. So these two notions of an A module and a representation are actually the same thing. And you can see that whereas before, for the representation, we did not really use the fact that these phi's of G's can be added. When we go to the language of modules, these phi's of G's, we suddenly realize that these phi's of G's can actually be a ring. And in this ring, we can add them and we can multiply them. And then this ring can be thought of as endomorphisms of this abelian group, which is really a vector space. We're just forgetting the fact that it's a vector space and remembering the fact that it's a group. And again, to repeat myself, these homomorphisms, which now we consider to, which we now remember that we can add them, they come from some algebra. And this algebra can be constructed by thinking of just the regular representation of the group. And that's the end of this video. Thank you.